All right, so if you recall, we talked about the idea of the adjoint of a one-step method. And so it's natural to ask then, is there a way of describing the adjoint of a variational integrator in terms of another discrete Lagrangian? And if so, how that adjoint discrete Lagrangian is related to the original discrete Lagrangian? Okay, so the adjoint, right, of a method and symmetric methods. So okay, so again, if you have given a one-step method, okay, so let's say psi of h, which is a map from say t star q to t star q, it doesn't really matter, right? Then the adjoint okay is denoted by psi star, psi h star, which is again a map from t star q to t star q, right? Satisfies the following, that the adjoint, okay, well, sorry, the time h map, okay, so the adjoint method, it's like with a time h step, okay, composed with the original method with a negative time h map, okay, is equal to the identity. Okay, so another way of saying this, if you will, is that the adjoint method is just the inverse of the negative time h flow, or let me rephrase that, the inverse of the negative time h one-step method. It's like, and what happens, if you will, is that if that one-step method turned out to be the exact flow map, then the adjoint of the exact flow map is itself. Okay, so the exact flow map is what is called self-adjoint because it is its own adjoint. Okay, so that's if you will, just a brief reminder of what it means. It's like given a one-step method to have the adjoint of that method. So now it's like it's natural to ask the same way that you can do error analysis of a variational integrator based on comparing the discrete Lagrangian to this exact discrete Lagrangian. It's natural to ask whether there's a way to characterize the adjoint of a variational integrator generated by a discrete Lagrangian in terms of another discrete Lagrangian, which then is naturally called the adjoint discrete Lagrangian. Okay, so I guess before I say that, it's like, so this is self-adjoint, right, or symmetric, if you will. Okay, if it is its own adjoint. Okay. All right. And it's always true that the adjoint of the adjoint is the method itself. It is always the case that the adjoint of the adjoint is the original method. Okay. All right. So anyway, so now let's ask what happens if you are talking about a one-step method. It's like generated by a discrete Lagrangian. So so if you're given a discrete Lagrangian, LD, which is a map from two copies of the configuration space to the rails. Well, I guess I should think of it in an extended sense. I should also include the time step here. So two copies of the configuration space. And the time step, so this rail part corresponds to the time step to the rails. Right. Then the adjoint discrete Lagrangian is, sorry, is given by the following, right? LD star Q0 Q1 H, right, is equal to minus LD Q1 Q0 minus H. All right, so what you do is that you replace every instance of H with a minus H, you swap the, it's like Q0 and Q1, and then you take the negative of it all, okay? All right, so so as you might expect, the same way that if you have a one-step method, which is its own adjoint, if you have a discrete Lagrangian, which is its own adjoint, then you say that that discrete Lagrangian is self-adjoint. So then LD is self-adjoint, right, if LD star equals to LD. Right, and then as you might expect, it's like from this other statement that the adjoint of the adjoint is always the original thing. It is always true that the adjoint of the discrete Lagrangian, right, and the adjoint of that thing, the adjoint of the adjoint discrete Lagrangian, is always the original discrete Lagrangian. Okay, all right. So let's try to prove that if you have a discrete Lagrangian and an associated adjoint discrete Lagrangian, then the one-step methods generated, it's like by these two discrete Lagrangians, are the adjoints of each other. Okay, so that's kind of what you might expect. All right, so I'm going to erase, it's like most of this, and then just leave the definition of the adjoint discrete Lagrangian there for now. Then we can get back to it. All right. Maybe I'll write it here in the corner. So LD star Q0 Q1 H is equal to minus LD Q1 Q0 minus H. All right. Okay. So let's just leave that in the corner, and let me state a theorem. Right, so if the discrete Lagrangian LD, right, has this discrete Hamiltonian map, which is F tilde LD, right, then the adjoint LD star of the discrete Lagrangian of LD, right, has a discrete Hamiltonian map right, F tilde LD star, which is the adjoint of the Hamiltonian map associated with LD. Okay, so let me just sort of be a little bit more clear here. All right, so here this is the Hamiltonian map associated with the adjoint discrete Lagrangian, and this is the adjoint of the Hamiltonian flow map associated with the original discrete Lagrangian, and they're related sort of in the obvious ways. Okay. All right. Then, all right. So, if the discrete Lagrangian is self-adjoint, then the discrete Lagrangian, okay, if the discrete Lagrangian is self-adjoint, then the method is self-adjoint. Then conversely, if the method is self-adjoint. Then the discrete Lagrangian is equivalent to self-adjoint discrete Lagrangian. To a self-adjoint. Discrete Lagrangian. Okay. And again, it's like the reason why one has to be a bit careful about this is that it is possible to construct discrete Lagrangians and then say shift them by a constant amount. Right, well, not a constant amount. It's an amount which depends. It's like on linearly. It's like on the time step, if you will, and then still get a still get a discrete Lagrangian which which generates the same flow, but which would not necessarily be self-adjoint, right? So one has to be a little bit careful and then talk about this idea of equivalence, if you will. Okay. I should say again that if you do construct your discrete Lagrangian in such a way that it is consistent with this Jacobi's solution at the Hamilton-Jacobi equation, then you won't really have this issue. But then more generally, one has to be careful, right? So because there's this sort of flex, if you will, it's like in the discrete Lagrangian and how it then maps to a discrete time flow map, and there's some non-uniqueness there which you have to worry about when you're stating theorems like this. Okay. Anyway, so let's not worry too much about that. Let me just sort of just prove this. Okay. All right. So let's consider LD, LD star, and their corresponding Hamiltonian maps. F tilde LD, F tilde LD star. Okay. All right. So for F tilde LD and F tilde LD star to be adjoint, of each other, okay, then what it has to be is that you have to have that F tilde LD Q0 P0 with a negative time step, right, as to equal to Q1 P1. Okay. All right. So all right, and F tilde LD star applied to Q1 P1 with a positive time step has to equal to Q0 P0. Okay. Right. And this has to be true for all initial position and initial momenta. Okay. So let's write down these conditions now in terms of the generating functions. So the statement of the theorem is perhaps sort of fairly obvious, so let's not worry too much about it. let's just try to see what the implications of these two statements are. So in terms of generating functions, what you have is that P0 is equal to minus D1 LD Q0 Q1 minus H. P1 is equal to D2 LD Q0 Q1 minus H. And then P1 is equal to minus D1 LD star and P1, right? So you have that minus D1 LD Q0 Q1 minus H is equal to D2 LD star Q1 Q0 and H. All right, and here it's just important to remember that when you have this D1 and D2, they're derivatives with respect to the first and second slots respectively. So in both of these instances, it is a partial derivative with respect to Q0. So D1, Q0 is in the first slot here, so this is a partial derivative with respect to Q0. This is D2, but Q0 is in the second slot, so this is again a partial derivative with respect to Q0. Okay, and then something similar happens here. D2 LD Q0 Q1 minus H is equal to minus D1 LD star Q1 Q0 H. Okay, all right. So more or less this is saying that up to this sign interchange issue, it's like there's a sign difference, and swapping Q0 and Q1, it's like that partial derivatives of these two discrete Lagrangians with respect to Q0 and Q1 agree with each other. Okay. All right. I guess what I should say then is that, okay, no, I should take a step back, right? So first I said that these two things, these two flow maps are adjoints of each other, and they correspond to some discrete Lagrangians. And then by writing down, it's like these conditions, it's like which are the definitions of these things actually being adjoint of each other in terms of the generating functions, you get this condition. And then this condition is more or less saying that, it's like these two things, right? So this implies that that basically LD star Q0 Q1 H is equal to minus LD Q1 Q0 minus H, again up to equivalence, if you will. Okay, so so one way to sort of think about this is that if you shifted this by a constant function, or actually a linear function in H, right, then the numerical method doesn't see that because it only takes the definition, it's like of the map in terms of this LD viewed as a generating function, only depends on the dependence, it's like of the discrete Lagrangian on Q0 and Q1. Okay, so if it's like, so equality, it's like in this sense, is all that is necessary in order for the maps to agree. All right, and so these conditions imply that you have this equality up to this notion of equivalence, if you will, which is relevant for discrete Lagrangians. Okay, so that's one direction. All right, so let's now look at the other direction, which says that, well, if LD and LD star are related, it's like in this sense that the corresponding flow maps are adjoints of each other. Okay. All right. So So let's see what happens. Okay, so if on the other hand LD star Q0 Q1 minus H is equal to minus LD Q1 Q0 H, all right, then what happens is that you get, so this implies, if you will, it's like actually these conditions. Okay. And then, as we sort of alluded to, this implies that the two flow maps are self-adjoint. Okay. All right. So that's basically what you need to show. Okay. All right, and then the issue about the self-adjointness thing is really just a consequence. It's like of following through the same kind of argument which we have here. Okay. And then you should, of course, it's like expect that in light of this, that the exact discrete Lagrangian is self-adjoint. Sort of remark. Let me just state this as a remark, right? Which is perhaps not too surprising. The exact discrete Lagrangian is self-adjoint. Okay, and then the other observation is that we already showed, for example, that if you have a self-adjoint or correspondingly a symmetric method, right? So self-adjoint is synonymous with symmetric, right? So if you have a self-adjoint method, then the order of accuracy of that method is even order. Okay, so so let me just make another remark, right? A sort of discrete Lagrangian, which is self-adjoint, right, has even order of accuracy. Okay, and you can sort of observe that, if you will, just, if you will, by the variational error analysis result together with what we know about self-adjoint methods in general having even order of accuracy, or it is possible to show this directly using this definition of the discrete Lagrangian together with variational error analysis. But I'm not going to go into the details, but I'll be happy to point you to a reference if you're interested in a proof of that. And let me sort of just maybe give you the simplest example, if you will, of adjoint discrete Lagrangians. Okay. Example. Okay, so if you have LD Q0 Q1, which depends on H, right, is H times L evaluated at Q0 Q1 minus Q0 over H, then you can check that LD star Q0 Q1 again with the time step H is equal to HL Q1 minus Q0 over over h. Okay. And then more generally, it's like as part of these alpha discrete Lagrangians, which we saw before. Right, so this is of course a special case where alpha is equal to 0 and alpha equals to 1. Then more generally, it's like you have that LD alpha, right? The adjoint of that, as you might expect, it's like just from this observation, is equal to LD1, well, sorry, LD1 minus alpha. Okay, and then from this observation, it should be clear that LD1 half, the adjoint of that, is equal to LD1 half. And LD1 half sort of generates the symplectic midpoint rule, right? And you might know, for example, that the symplectic midpoint rule is symmetric, okay, which you can see from this result, so which is symmetric, and it is second order accurate, okay. Okay. All right. So let me just stop here for now.